Okay, today's lecture involves the introduction of force fields, and doing that just with the axioms, theorems that we've sort of created already by studying the bouncing balls in one dimension. And these will be one-dimensional force fields that are introduced here. The basic idea of all of this, of course, is to have a logical efficiency, and also to compare that logical efficiency to, hopefully, a logical efficiency for quantum theory, relativity, all sort of modern physics. The things that we'll do for sure today on this duty list here is introduce the pressure idea. So this is a little bit of one-dimensional statistical mechanics that's going on here. And the other thing is to distinguish the physicist's definition of force fields and potentials with the mathematicians, and thereby avoid sign errors that occur, but also have an amusing way to see two different ways of looking at things. When we get to chapter 10, where we review complex variable theory, we will be looking at them as fields. Any function you name makes a beautiful picture of a coordinate system, some coordinate system that you might otherwise find bewildering. It becomes very simple. But that coordinate system is also field lines for electromagnetic, hydrodynamic, other things that we don't always talk about in graduate courses in the United States. Now, at the end of this, I'd like to show something that's really quite funny. And I mean, it's amusing in many ways. And it also has a wave analogy attached to it, which we will review when we get to Unit 4 in more detail. But I thought you ought to see it right away, just to be aware of some of the things that are coming attractions. Now, this is something that came from the AAPT that I mentioned before. There's a book called, in fact, I even think I have it up on the shelf there, called Thinking Physics. And this is written by Lewis Carroll Epstein, which is kind of a weird name for anyone. But Epstein also wrote another approach to relativity that's very, very interesting. He and Paul Hewitt were fantastic teachers. They were at the San Francisco City College, which was a kind of a feeder school for Berkeley. If you couldn't get into Berkeley on the first pass, you went to City College, and these guys would get you so you were in good shape to go to the physics department at Berkeley. Anyway, this is just one excerpt out of the thing, a whole book called Thinking Physics, which I recommend to you if you're teaching, even at high school level, but certainly at college level. It can take the anxiety out of physics for people that are having anxiety. In any case, this is one question that I'm not sure I agree with the answer that he gives, and I have been trying to find this particular episode somewhere and see what answer he does give. We'll talk about this midway through this discussion of the bouncing balls, which we've already seen the simulations of it, and basically we're just going to take that model to do what I was just talking about, develop force fields. So this is the starting part of this right here, and go ahead and put it up on this screen here as well. Basic idea of our, say, Super Bowl, now turned on the side, and maybe we're going in an air track or something like that. And there's this very small ball that is just getting knocked back and forth. By this one's motion, we're going to imagine that it's closing in on that ball. And we've seen from that picture at the very end screen down there that there's a lot of bouncing going on when you make the distance that the ball lives in small. And then if nature takes its course, as it does in that simulation there, finally this one manages to give this thing enough momentum so that it stops having positive momentum and starts to come back again. That's the trajectory
that you see there in that simulation we did before. And just out of curiosity, how many people have actually tried to run these animations, particularly that one? Has anybody here actually making your computer do that little thing there? I'm I'm surprised. You've tried it, yeah. Well, I recommend you do this. I mean, take a look at these things. They're worth seeing and playing with for sure. In any case, the idea is compress a volume of gas, and it gets hot. Release it. It gets cooler. Assuming there's no other way for the energy to get out except into one of these two objects. So this is a sort of a one particle gas and a piston, or what are you going to call that, M1 there. So here's the deal. When the thing is got lots of room, lots of space here, a large value of capital Y here, and we're imagining we're in some sort of box here, and this is the origin right here, so we're looking just at that particular point. This is some height. The thing was turned the way we've been running our Super Bowl experiments that way, so this would be H minus Y, and this is Y positive that way, which is kind of an unfortunate thing, because usually you think of the left-hand side as being minus. Bear with me on that one. In any case, the idea is that the trajectory of this ball going back and forth fairly slowly and taking a long time to make a trip isn't giving much of as much momentum to this ball as that one is when you have what I call a double whammy. And that is that now these guys are really going fast, so the momentum transferred on each hit is more, and also there are more hits in a given amount of time. That's what I mean by double whammy. So we're going to play both sides of that double whammy sort of in concert and separately with some approximations. And that's what this is all about here. So, as I said, this is our first introduction in this particular course to force. And I would like to emphasize that we already have a definition of force if we think of how much momentum we get hit with each one of these things, that we already sort of can feel the force that this is going to be experiencing. But in just this as a definition, this is more of a definition than another axiom. We're going to be using all of the momentum and energy knowledge that we have so far to carry out this vignette here. So here's the introduction. Force of F on the large object by this smaller object, presumably smaller, although there's no definition there, but to make it more like a gas, we have to think of it as this is an atom and this is a piston, then there's a tremendous difference in size between those. But this would still work when they were comparable or even flipped the other way. Now, this momentum per second transferred, that is, we call that force, that's the definition. And the change in momentum, that is the change between the in and the fin for one bounce, just using that right there, is that change. So the momentum per bang, and then the number of bangs per second, that's what's going to be giving us the force here. And the bangs per second is an inverse in time, 1 over this delta t, which for just looking at this around a particular instant, we're imagining the delta t is something that's eventually going to be variable, but right now is sort of a constant number of bangs per second. If this thing were really going fast, that would make sense. Now, I want to emphasize before I go on here just some of the sort of philosophy behind this thing where we want to make sense out of quantum mechanics. Note that the very first axiom of quantum mechanics, Planck's 1900 paper, deals with energy, not momentum. Okay, here we're kind of forced, so to speak, to deal with momentum first. Okay, so there's a big difference between the sort of our logic of going at classical mechanics and the logic which we'll introduce later on, at the late in the course, in fact, where frequency, energy are, except for scale factor, the same thing. Okay, and I'm going to mention this thing again later on in this lecture today, just to, keep that line of thought going. In any case, this was kind of the first diagram we made if the mass ratio was really pretty high. If we had a slope of the collision line really steep. That's a big ratio, M1 to M2. And so we're talking about infinite slope almost. And if you approach that, then what you notice in each collision is that you increase by twice the V1. Twice the V1 again after the next one, and so on. It's always jumping by 2 of these squares, where that was the initial velocity that these had in our superball experiment, which is 2 things coming down to the floor. This one changes direction before they hit, then they hit, and this one takes off. This thing's really massive, then this thing takes off with an extra 2 times the velocity of the thing that's hitting it, the big thing, assuming we ignore its recoil. That's why I'm suspicious of the answer in that Hewlett episode. Okay. Bat, ball, much lighter. Okay. Certainly tennis racket and tennis ball much lighter. Okay. Definitely increasing energy more than what he's letting in on that choice of 4 answers. Okay. Now, all of this has to be put together in something that makes up an equation that we can use for the force. And basically we're taking, for M1 quite a bit bigger than M2, we're taking here this extra 2V1 here that's being added to that, and here I'm just taking the magnitudes of those, but it happens that the equation can be written without the absolute value sign. So the final velocity, this minus, it gets an extra minus V1 in this direction. Okay, that's what's happening to the M1. So we're asking the momentum going into that big ball, what does it come to? And we go ahead and put this little part here, right here for the final velocity, V2, after just one of these back and forth, and end up with something like that, 2 times M2 V2 Vn, plus to whatever V1 is at that particular moment in the collisions. Now, assuming a very slow M1, just creeping compared to the little guys, and that's your statistical mechanics of gases right there. We talk about, moving the door or the piston on some, or just squeezing a balloon. That motion is so very slow compared to room temperature motion. We have thousands of kilometers per second for actual velocity of oxygen or nitrogen in the atmosphere. So V1 much less than V2 is an approximation we're taking right here in this one-dimensional statistical mechanics lesson. So here's what you end up with for the force, that is the change in momentum per time, is something that has these things again, once again, approximately equal to V2 over 2y. So you end up something that's very similar to what you get when you read about this in statistical mechanics. And that's the mass times the velocity squared of the little thing that's getting kicked up here, divided by the volume, you might say, but the length that it's allowed to move in. Okay, so that's our force law right there. There's a force as a function of the distance between the 2 walls, the wall made by M1 and the wall that's just stationary, this thing right here. Okay, does this make sense up to this point? Okay, and I'm using blue color here for the typography because I'm talking about the situation when it's fairly cold. So it gets to be hotter, and that's something that's going to happen in another approximation here. We'll get some different results. Now, as I've promised to move things ahead on at least both of these screens, and maybe on this one as well. So here we are at this particular juncture with, up at the top, the results that we have for this. Now, I would call this the isothermal force law. And what we're doing here, if we write this equation out, is we're assuming that V2 is constant. And you see from the pictures, like the one with the guy on the right on that screen there, that's not always going to be the case. If I come in here and this guy comes in fairly quickly, there's not going to be any way that this thing can cool off. That is, any way that this V2 can be taken down to what it originally was, and therefore treated as a constant. So that's basically what we mean by isothermal. We mean that the V2 is somehow going to, some kind of thing is going to help it get cooled off after each collision. And V2 is still fairly small, in fact equal to what it was here in an isothermal force law, which is what that is the simplest example of, a one-dimensional isothermal force law as a function of the space that's, remember, the big Y that it's allowed to live in. So we want to carry this a little bit further, and this gets a little tricky. What we want to do is get the red one, the red formula, the formula that has to do with what we would call adiabatic. That is, what do you get when you have a chamber and you do something that doesn't give it time to equilibrate with its environment. So let's carry that a little bit further here. This is where, as I say, it gets a bit tricky here. Okay. The ceiling is elastic. V2 isn't constant as M1 changes the space Y, the bounce range, the volume, if you will, of the thing. And we're interested in the time derivative both of the Y1, that's this distance right here, or big Y, okay, the derivatives of those are going to be, except for sign, the same. And we're having that V1 be the actual velocity of the thing that's making the space allowed smaller. This is standing still, but this is the one moving here at V1. Okay, so M1 collides with M2. It adds twice the velocity. That's the thing we notice in our first day here with collisions of two masses. And the bounce rate, that's always going to be this, but this will change. Both the distance y and the velocity are going to be doing some changing here. So you end up with a pretty simple equation for this. This is the 2v1 bounce rate. There's the bounce rate right there, and then some things cancel here. The 2 cancels, I'm left with a minus, okay? But I have a dy over y. I can get the dt out of there completely and get an equation just in terms of y and that velocity number 2 that we claim is now going to be changing maybe quite a lot. So you end up with a calculus problem, an integral of dx over x, logarithmic answer coming here. So this little thing integrates to a logarithmic equation, which you have a logarithm of this v2 that we're after, and then the logarithm of a constant over y. Now, what's the constant? That's going to have to be set by initial conditions and all of that. But the basic idea is take the logarithms away. This is not such a multi-valued function we have to worry about the logarithm doing anything. The velocity then comes to be simply a constant that was started in the original, and as you squeeze in, inverse to the space that you left it, you're going to see the velocity increase. That's the adiabatic case. Okay? Now again, I'm not keeping up with everything here for the 2 screens, but that's kind of the answer we're really looking for right there, in which you state what you started with and what it's going to be at a certain time later on. So these initial values here are a constant. And look at that. What a difference. What a difference between 1 over y and 1 over y cubed. That's a heck of a difference. Okay, just in terms of the functions. So the adiabatic thing I'm writing in red is pretty steep is what it amounts to here. This is a real double whammy now. By double I mean it's getting fast because it's contracting, but it's also getting fast because it's getting hit harder. Okay? It's quicker and harder. I'm not going to patent that expression. Okay, now here's the idea though. In all of the collision stuff that we've been talking about, if you're really talking about closed systems and you're talking about things that collide elastically, this is a constant. You see, this is the trick to this whole thing here, is that the sum of those two is a constant. We got one thing here, a super ball, it's going in. Now this thing is getting hit lots of times, but all during that, we're on the same ellipse, same total ellipse. Okay? So this is where we make the very simplest axioms, the axioms of momentum, work for us and give us what you're kind of used to already. You've learned about UP having kinetic energy as well as potential energy. You see, it's just that the potential energy now is the energy, kinetic energy of the M2. Okay, does that idea make sense? That's kind of a sneaky way to get into the thing that just throw at you every time. T plus V, right, is your total energy actually, Lagrangian total energy, because you're giving it in terms of velocity as well as the coordinates. We've got one coordinate here, right? Okay, so that's what we're going to work with. And this is the hardest case. The other one is the isothermal. We can work with that one too. But let's just go ahead and look a bit at what we can say about potential energy functions. Potential energy field. I mean, you've got a field as a function of y here, okay? I'm the big ball coming in. I can feel this field. Oh, it hurts, it hurts. Right, not back off, right? Doesn't hurt as much, right? But you don't actually count the bounces when you're talking about this kind of thing. It's going so fast that it's continuous. So you're feeling a continuous force field here. Okay? All right. Now, is this another axiom we need here? You've all learned about work relations, okay? F dy equal d potential energy, du, okay? That can be plus or minus, as you're going to see. Depends on who you are, you physicist or you mathematician. Okay, but in any case, a question, is that another axiom? Okay, I already dismissed the definition of force as another axiom. It's just a definition. This one we already can calculate. This is, you can either do it integrably. The answer is no to this is another axiom. Integral of f dy is integral dB dt. So this is something we've taken as a definition. And then we turn it around and we do just flip these. That's something we do in calculus. So we get a v dp. We get a velocity dp. That's a velocity dmv. Okay, which is the same as v squared over 2. Okay, that's the integral way of doing it. I'll probably sneak here to do this, and this is actually the little algebraic step that is the hardest part of deriving the Lagrangian the way it's done in most textbooks. But this is the sneaky little thing that Lagrange does to turn up the Lagrange equations later on. we'll do that in the review chapter as well as when we get to doing this stuff in Unit 2. But anyway, dy dt, okay, that's the actual change. Well, it turned out to be dBt times v. And we can turn that around, and finally you get to this thing right here. There's your mv squared over 2 right there. That's just the little sneaky trick that's going on here. This is that, and that's du dt. Okay, so you're basically getting this result again another way. Right, so that's a sneaky little thing right there, Lagrange's sneakaroo. Okay, now let's go back to the hot one, the adiabatic one, the one that has a pretty impressive y cubed force law, inverse y cubed force law. And let me make the distinction between what physicists are used to, and which involves a minus sign, and makes minus, 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 and gives you lots of minus signs. Mathematicians said, I don't want those minus signs, and they're kind of the ones that first invented the idea of fields, and this is the thing I referred to before that we're going to do in Chapter 10 of Unit 1, where we investigate complex functions, each one giving us a field, a two-dimensional field, and not just one dimension, like we're having here. And they define their potentials, their whole book's on potential theory in mathematics, okay? And it's always a plus sign. Always a plus sign. Okay? So what does it mean? What is the mathematician thinking? The mathematician is thinking about what it would take for him to hold the mass at a particular point in that field. Hold it back. And you need a force this way if the slope is this way, right? But the physicists said, oh, no, come on. Let it go, right? They always put a minus sign. Okay? Hence, I think the reason for them, the mathematicians being called constipated mathematicians. Hold it back, right? Physicists, just let it go. Whatever crap you have, just get it out there, right? I mean, that's the difference in the cultures, too. Okay? So let it never happen that you forget to put the minus into this, because that's the way we're mostly going to do it until we get to Chapter 10. Then we're going to go that way, because I just don't want to have a bunch of minuses all over the place. So this is more efficient, certainly. You don't have to write minus signs all the time as much as you do. Okay? Okay. Well, that's pretty much the main message of what we need to know for today. The question is it consistent? Is this consistent? Is this potential discussion here consistent with the force, crazy force that we've got here back on page, and it's actually more than that. I forgot to change that number because I put some more stuff in. It's probably on page 19, but it's not far from there. Anyway, for this double whammy system, we've got a force law. And the question is that the force law that's working up here? And it helps to go ahead and see if that's the case. Does the minus the derivative of this thing equal to this force? Okay, and yes, it is. It is very consistent with that. The twos cancel, and we're off to the races here. So, hurrah! This thing is consistent in that way, and the derivative of the potential with a minus sign is giving us the exact force law that we calculated by bouncing. Okay, again, I'm failing to keep up with the middle of the room here, but that's the basic idea right there. Let's see if there's anything else. Well, we're going to do the isothermal too, and that's kind of crazy. But for the adiabatic, we're letting the M2 pick up speed as we close in on it. Isothermal, It's kind of like more like an economy. You have a Federal Reserve that sits there, and when things get too hot, they take money out of the system. When it gets too cold, they try to put it back in. If they were really skillful at doing that, we would never have crashes, but unfortunately they're not skillful. They're political, so expect crashes. But that's just an economic message that I hate to give each year, but it has certain truth to it. Okay, so let's take the isothermal one, and suppose this is true, and does it really work? Does this 1 over y force here work for a potential, okay, that's this? So we have to check both sides of that story. That's not too hard to do, but I just thought it would be necessary to do it. While we're doing it though, this logarithmic potential, okay, and that's the one of the first that we're going to look at in chapter 10 when we look at the complex logarithm. You'll be seeing a sort of a morning glory, or it looks like a black hole potential or something. There are lots of sketches of what it looks like getting near a strongly gravitating object. But in any case, I just wanted you to see this logarithmic potential here and how really it just snuggles up to the potential axis, right? Very much more than the other one. I just want you to notice how tightly it hugs there. Let's get it on this screen as well. And so much more than just 1 over the coordinate. 1 over x, right? There's lots of room here to fall in. Nothing here. Okay? So just be aware of that. Of course, you turn your head to the side and flip it over, it's an exponential curve, right? That's called taking the inverse of the exponential is to get the logarithm, right? And vice versa. Okay? But be aware that as a potential, it just cuts you off at the pass here, right? It's decreasing exponentially, right? Whereas this guy, lots of room, all right? And you can trust that plot to within a pixel, right? That's the way it looks. And these are the things you should always do with any function you get. You should play with it, massage it a little bit, love it a little bit. It'll return you love, okay? It'll give you stuff, all right? Just writing it down in an algebraic equation, never looking at the roadmap it makes, that's no fun. Why do we do things that way? I don't know, okay? But don't do it. Be better than that. So anyway, we'll go ahead here and take our Lagrangian, this simple Lagrangian with a 1 over y, now 1 over the coordinate, and then one velocity variable, that's the big M1 that's experiencing all the bouncing of the tiny little thing that's making the potential, the V2, as it were, okay? So here's the hold it back, let it go. Now we're just thinking about, is this consistent? And yes, of course it is. If you know your calculus, it's all working out. This force here is the minus the derivative physicist force. Now, and the ball wants to go that way with the logarithmic potential. Now a potential just snuggles up, goes flat on the way out. Okay. Well, I think that's pretty much all that we need to talk about with respect to this, but we'd like to use this result a little bit. And I mean use it in some simulations of something that is being bounced. Not just one little hot mass or medium hot mass, but another one on the other side. This is going to be in a box now. And we'll start off with the easy one. It's just F1 over y. And we'll work out that, and I'll have you repeat that on a problem coming up here. But I also ask you in that problem to do the adiabatic case too, just to compare them. Remember, there is a terrific difference between being 1 over y and 1 over y cubed. So you get to see what that difference amounts to. But here we're going to be using not just the logarithmic potential to push this thing that way, but I've got to have another ball it makes a logarithmic potential on the other side. So we're going to have two balls making potentials from both sides now. And result will be some curve that has a bottom to it. In other words, a curve that actually wouldn't just explode quasi-exponentially, but one that would have maybe some sine and cosine oscillations inside this trap, a double trap, you might say. So I've got walls that don't move on both sides, but then I've got something moving really fast that's making force on the big mass, M1. So here are the two opposing isothermal force fields. Basically, one plus x and one minus x is all you're looking at. Those two summed together. Now this would give you an expansion that looks like that. Let's get this going here as well. Now, as you put these together, you're going to be seeing that the for small x, all I'd have to worry about was this first guy here and this first guy here, and then I don't have to worry. I mean, basically, let's just write this out in its entirety and do that on this screen as well with all of the things exposed. Okay, you'll notice there's a good deal of cancellation, odd terms. Even terms. These guys, this cancels with that, this with that, and then if there was another one here, you cancel with that. So I'm just left with the odd terms here as the in the force totals there. So in case you weren't keyed in here today, we're just using binomial theorem with n minus 1 here. So these are series you should be aware of, just on general purposes. This one particularly, and that one right there. So those are the two that we're adding together to make the force law. Now, if I keep my amplitude down here, if this thing doesn't start out and just bubble its way toward one of the balls or the other, I'm going to be able to, and we do this all the time in all kinds of physics. Molecular physics is famous for dropping the anharmonic oscillator term. This is a harmonic oscillator. This is an oscillator which will eventually be anharmonic. That is, explain what anharmonic is to you once again, but it's basically something that has a single frequency and hold dearly onto it. This oscillator term right here is the one that we're going to use to calculate what we'll actually see in the simulation. Simulation of this doesn't know anything about oscillators or potentials or anything. It's just bouncing. So we're going to let that happen. Now, I'm deciding right now what computer to use, and I am going to bring this one up to speed here so that we can play some simulations together. I think that may help see some of the phenomenal stuff that happens during these simulations. And that screen right there is showing what it is that we're dealing with if we ignore the anharmonic part. We don't have to worry about that, and that is so common in many different fields of physics. Sometimes the only thing you really can calculate easily is the harmonic part. And you can see it's kind of a nice thing. It's basically the kinetic energy associated with the perpetrator of the field, the little m2. Basically, it's not 1/2 mv squared, it's 2 times that. So 4 times the kinetic energy divided by the y0 that it would be deviating from the origin. Now we thinking this is our origin. So this side, I've got a force. It's a Hooke's law force. You've got to get Mr. Hooke, Robert Hooke, Newton's nemesis, into this classical mechanics early on. This is Hooke's constant here, and Newton didn't like Hooke very much, so he never called it that. But this partial derivative we talked about is the physicist's derivative force law. And the potential, well, you've got to integrate the thing, and that's what you get. Okay, so this is what we're talking about. The physicist's favorite problem. The problem with any number of dimensions, the physicist can do this easily, because the harmonic oscillator potential has a tremendous symmetry, the hugest symmetry that you can have in a bound system, and that's the unitary group. And for that reason, it's easy to solve harmonic oscillator problems in all kinds of different ways. Add any anharmicity, and it's a good chance the symmetry is completely broken and there's no analytic solution that's nice and closed like you're used to. So thank the group theory when you can solve something. All right, so we'll be talking about that plenty enough. But anyway, this is the thing down here, whereby, just by knowing M2, whatever I pick for that, whatever V2 I started out with, and of course M1 is the thing that's actually getting treated to this potential. From this you can get the frequency. We're going to see if that works out here, because the simulation that we'll be doing will not, excuse me while I jump this one to this particular point. What does harmonic mean? Okay. Given this total energy where both variables are quadratic, the velocity and the position, the coordinate, okay? And that's going to be true to go to Hamiltonian, put momentum here, it's still going to be p squared, right? The m will be in the denominator with the two, okay? So having both the kinetic and the position being the same power, high symmetry. You switch them and it still works. Okay? So, what we're talking about here is an energy that is the same function for any amplitude of an oscillation. Okay, so if you're trying to explain this to a high school student, what sort of motion that we're going to get, you have to teach them a sine and a cosine. If you assume a sine, you get the cosine with an omega here, the derivative of y with respect to time. Okay, so we end up with a cosine squared and a sine squared. And then there's an m here and there's a k there, but you sort that out pretty easily. Okay, this one comes out to a squared omega squared and k a squared sine omega squared. Well, that comes out to this thing with omega squared a squared and 1, right? Bingo. Okay. So there is the basic energy expression, and it's only a function of frequency and amplitude. It's telling us that our classical energy in an oscillator is that simple. That's really cool. That's lots of symmetry behind that. But here's the thing that I would like to bug you with, and this must have bugged Planck. It is understood that when he first proposed this thing for electromagnetic oscillator, that is the harmonic oscillator of all harmonic oscillators, is a cavity in which some mode is going there at so many terahertz. If it's a little optical cavity or infrared cavity, it's hundreds of terahertz. If it's a color you can see with your eyes, okay, you have something going on in the vacuum that's an oscillator. That's Maxwell's equations, what they ultimately say about that, okay? How can it be that the energy that is ultimately true for that quantum cavity is a constant times omega to the first power? And Planck must have looked at that and gone, dumbcock, why did I make this stupid axiom? It worked, it gave the distributions that you needed, okay? Turns out it's right, but he didn't. He said, I've made the terrible mistake, I'm going to go and sell shoes or I'd kill myself or something, right? Really depressing. So I ask you, how do you save Planck? Okay. We're going to talk about this throughout the course. There's not an easy answer. I mean, there's a flippant answer I can give to you right now, but I'm not going to do it. Let's think about it. Okay, let's go try some of these simulations. Any one of these computers is good to go, I think. Even this one should be good to go, okay? So just for the heck of it, take the center one here to start the thing off here today. And this is a situation where I have 1 to 500. Got to see the little one guy on this side, little guy on this side. Okay, this looks like a disaster. This don't like that, right? Well, let's just see if it works. I'm assuming the computer's gonna be good to us. That's really the only thing I worry about. There we go. I gave it a little bit of an M2 initial condition there. And now we're calling this one M1, this one M2, and that one M3, so don't confuse the numbers on the particles right there. And we're keeping track of the velocities in between bounces.
Close those other windows out, Professor.
15.1. Pardon?
Close those other windows out. They might be drawing your CPU down a little.
Go ahead and do a view.
Just close the other windows, those tabs.
Oh, okay.
Because if any of those
Yeah.
are running, you're going to be
I
sharing.
close this guy
CPU.
here, right? And this guy,
Mhm.
and this guy, okay? And then resume
But
here.
it actually didn't
Oh,
close.
I turned the wrong one, right? I turned this to a different, I turned this back to what we were doing yesterday. Okay.
Yeah, quit
So,
the whole thing and relaunch.
Let me, let me go ahead and just get rid of all of these things so we can have more room. There's what it's doing now, right there.
It's
But
swelling up.
wouldn't hurt, I suppose, to enter full screen.
It's the other rack.
There. That doesn't help all that much because I've got to get rid of that stuff. But let's go ahead and just resume. You can always, whenever you get in trouble on one of these things, just reset t equals 0. But you can see now this guy's a little faster than this guy, so he's pushing him back. But as he closes in on this guy, he's going to get faster. And it's that simple. There you have what is really a one-dimensional gas with 2 atoms in the gas. Okay? That's cool. It's also a horribly chaotic system. You start changing parameters, making this thing do a lot. That's why I give you these things to play with. You can see that it becomes a chaotic system fairly quickly. Let's see if I have some other ones here. Now, before we go on, this particular one is asking us to calculate the actual frequency. What is the harmonic frequency of this system? And its low amplitudes. Okay, we've got to put in Y0, we've got to put in the velocity we start with, the mass ratio of that 500 to 1. That's there. Actually 50 to 0.1. That's this ratio right there. Okay. And what I get is a period I can measure. This is time here. I get a period of 17.38. And that ain't what I'm seeing here. That's not what I'm seeing. Okay, so maybe something else has to be done here. Okay, this is about square root of 3 times 2b. Well, that's included your homework. This thing is an isothermal. This is adiabatic. The simulation here is adiabatic. No Federal Reserve to cool it off, okay? Or heat it up when it's needed. Okay, that makes sense? All right. So we've got for time here. This one is large amplitude. So this is the one that's interesting in the sense that it would go chaotic more easily than the one that we're looking on the center screen here. Let me just see if this computer is up to it. I'll just click on there and see if it will pull up for us. Yeah, see, this one is a much smoother ride, but still, it's in an area where it kind of makes a cosine, sine curve, whatever conditions set it to. But you start raising the initial velocity of m2 very much, and it will go crazy. Anyway, here's a list of what you get when you go to the control panel on one of these scenarios for this app. You can change just about everything and play around with it. Okay, I'm going to go ahead on this one. You can see period adiabatic force. This one is kind of neat. Well, what's interesting is to notice, and this is something you can do very easily, is draw a line and see how well is that cosine mirroring there. You see it's drifting a little. Okay, and this is one that has lots of bounces, but nowhere near the amount of bounces that it would really have in a real gas, right? We're operating with a very small number of bangs and getting quasi-continuous motion. Okay. All right. The rest of this lecture is just for fun. But it connects some stuff in wave mechanics and analogies. And here's the other thing it does is this is where we see the conservation of another kind of variable that's really important in quantum mechanics. It's called action. It's basically a product of velocity and momentum, or an integral of a differential involving velocity and momentum. We'll define it more closely later on, and in fact derive that idea just from wave mechanics. But what we're going to see here is the uncertainty relation, the product of the range of a coordinate and the range of the momentum. In other words, we're going to see a classical uncertainty relation. This is Heisenberg's idea, comes much later than Planck's. Okay, but it's just a bunch of balls bouncing. Okay, well, it's not a bunch. It's one getting crunched, as I call it. The name for it is obscene, really. This is abuse. This is terrible abuse. This poor little ball here is going to be pushed by something that's infinitely massive. Okay, so here it is standing still. Here's the trajectory of the ball, okay, minus radii of each of them, so we could actually see where the center of each one is on the time graph. Time now is down, okay? And you know this has a velocity 1, that's a unit slope right there, okay? This has velocity 0, but it's going to pick up how much? How much does it pick up? And don't listen to Paul Hewitt, but listen to our little graph for the case of infinite slope over here, where we picked up 2v1, right? v1's 1, so it's going to pick up 2 after a collision, right? So this thing's coming through here with a slope of 2 to 1 in space and time. Okay? Then it bounces off on this side an infinitely massive wall, lots of infinitely big things here, and comes back with -2. Then it runs into this guy that's now reduced to space here from delta x equal that to delta x equals that, and immediately whacks it another 2. So it goes to 4. Okay? And then it doesn't take it very long to run into the wall and come back. Okay? With a -4. And then another 2, so it goes to 6. comes back with a -6. Gets another 2, 8, comes back with a -8, and so on. 10, 12, 14. It's an implosion. That's abuse. Can't do much worse than that. We're crunching this thing. Okay? But the idea is that no matter what scale I look at, I'd see a diagram something like that. So if you extend the lines of this, and I'm going to ask you to go ahead and construct this thing in some detail, you find that all of the trajectories on either going this way or that way, the ones that are going that way, all intersect down here at 3 units from there. Remember the 3 that came out of infinite mass ratio there. And the other one, the come back trajectories, they all intersect right here. So this monster mash, as I call it, does that. Now, the connection of this to uncertainty is just as I cut down the range of the coordinates that it has, the momentum goes up and the range of momentum goes up, so that roughly speaking, delta x, delta p is some, well, maybe huge number times the Planck's constant. In other words, this is really what Heisenberg's principle looks like when you're looking at a classical object where the quantum numbers would be astronomical. And it's good there too, it has to be. It isn't just good when the ends are onesies and twosies. So that's kind of neat to actually, have that. So what you see is a decreasing space, increasing speed. As I decrease the speed gets bigger. Delta P gets bigger proportional to how delta X is getting smaller. All the way, in this case, to absolute oblivion, crunch, right at that point. Okay? Now, the animation of something like that is not too telling, but let's just run it anyway for the sake of argument here. Let me go ahead and return to the lecture on this screen here, go forward to the point where we can actually animate the portal crunch. And this is just so you have a quick movie picture. There we go, okay? Bang, 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 okay? And the simulation is good enough that it can actually return you and make it do it again, but by that time the time is over, so you won't see the time graph of that, but there is the monster mash for what it's worth, okay? This graph here is probably more telling, and that is that the area, the phase space area, x versus p, well, velocity versus coordinate, is constant. Okay? All right. There's the kind of the picture that we had. And this one right here, I think we'll just do the same as what we've seen there. So this is the velocity plot being shown there. So this is the kind of graph that I'd like you to make, but I'll give you a particular velocity that isn't zero, see if it works for that, and how much it works. And then also notice that when you do some geometry of it, and this is all in the textbook, when you do some geometry of it, you discover that if you just extend those things and then draw another set of boundaries, you could have that going on in here, and it would be exactly a mapping of what's going on here. And then you can balance the whole thing so that it's the same on both sides. And then you get a diagram that's like this. And so if we have 15 more minutes or so, I'd like to play a few, I'd say a few things about what's going on here. This is what I call the tiny Big Bang. And I'll explain what I mean there. I mean that I have a one-dimensional universe, well, two if you count the phase space, And let's go here. So this is the name, a wave analogy, tiny big bang. Okay, and here we start with a wave function on the simplest quantum mechanical problem there is, the one that you get in a sophomore physics course, and it would simply be a particle on a loop, on a ring. Okay, no potential, nothing, it's just kinetics. Okay? And what I do is I make a wave function that's a Gaussian, or some other function that's narrow, could be a Lorentzian, but Gaussian is much nicer because it goes off e to the minus x squared, so it really has very little probability any distance from the thing. So if I make a Gaussian that's that big, there's virtually nothing anywhere else. So what we're going to see is a wave that starts completely at one point, that is completely at a point on the other side of this cylinder. This thing right here needs to be wrapped and glued together on the other side. So what we're looking at right here is in the front, and we're going to start a Gaussian in the back that's really small, okay, really tight, has a really small delta x. And you know what that means. If you have a really small delta x, you've got to have a really big delta p because the product's going to be a constant, right? So basically, when you make a small delta x, you're making a bomb. Bang, right? It's just full of all velocities. It just wants to get the heck out of there, right? But in a beautifully coherent way. So coherent that eventually it reforms. Actually, it reforms on this side and then forms on the back. This is the Bohr orbit, simple Bohr orbit. No radial apart, just angular. Just this. Wave function on a circle. Okay? Can't get any simpler than that. All right? Has a quadratic spectrum, and that's what makes all of this happen. Okay? So that's what I'd like to show you. And this is just a picture here of what we'll start off with. We'll start off with a Gaussian wave that is at the North Pole, and there it is. This is this thing unraveled to that size. Okay? So what I will be doing is I will be clicking just the set t equals 0 on this, but I have to actually get it up on the screen here. Maybe I go ahead and leave this one to show still lifes.
Use the
And I'll
FAR
go
one.
on this one. Pardon?
Use the FAR unit because it's much quicker. And you
Okay.
recall the carpet lays out real
Okay.
slow.
That's fair enough. Let's get this one shut down here.
Do them both. But
I don't know how far it's, I think it's gotten all the way to Fort Smith by now. Let's just pause this guy and then I'll return. And I've got to use this one right here.
quick.
There we are. And I will go forward on this one until we get to the tiny Big Bang. Okay. So here we go. Let's just try this one. See if it's fast. I'm not sure it is, but it won't make any difference. It's better to see it sometimes slow. That wasn't what we wanted. That is definitely not the particular wave simulation we're looking for here. See if
Quit.
something crazy is going on there.
Just quit.
Probably a bad choice because I haven't upgraded that one to local. Let's go ahead on this one right here and see if we can get it to do the wave simulation. No, that's weird. You might try playing with it because of, I think what is the scenario number probably is what we're getting at the beginning fun on.
Apologize on that one.
Yeah.
I twitched it.
this thing is full of all sorts of wave programs. We're looking for, probably at the bottom there.
Yep, here it is. We'll do the boxcar first.
No.
With this, okay, Gaussian with distribution.
Yes.
Because we don't have the time.
There we go. Okay, get out of the way here. It just blew up and went around, started interfering with itself at the South Pole, and then is interfering everywhere. Now it's just a dance showing you different symmetries that it can produce. And we can produce all the way up to about 10 or 11 or 12-fold symmetry. Half of that. We can produce 5s to 6s to 7s. And you'll see that was a 7 there, I think. Anyway, all of the rational numbers that have denominators smaller than about 7 will have signature on this thing as it rings around its little universe. And this is the Gaussian distribution that makes for a really clear picture of the same sort of trajectories, but now trajectories of zeros as the monster mash. And there, it's all forming on the South Pole just briefly, and now it's just going to repeat and reform like that way up here if I let it go. But this is where it stops. Okay, just that. And that's fast enough to, get it where we've got the thing. Now, what is it that's going on here? There's a lot of really beautiful number theory. And I'd hope this would have something to do with quantum computing. So far, it's not turned out to be useful for that. I mean, basically, this is just stepping through it to show you what we've got. Okay, there's a typical 3/5. Whenever you have a fifth, 1/5, and then 2/5, and now it's 3/5, you get a little pentastar, okay? A 5-fold symmetry, okay? All of the symmetries, you'll even be able to see, if you look really carefully at this moment, you would see 11. All of the odd numbers give you the symmetry that it says. The even numbers, you have to divide the denominator by 2, and then this is going to give you a 2-fold symmetry. This one's going to give you a 3-fold symmetry instead of a 6-fold, you see. This one with an odd number is going to give you the 3-fold sort of honestly. And you can see it there, 1, 2, and 3 peaks. Those are peaks. The white regions are zeros, or near zeros. Okay? So, real question is, and there's a typical 3-fold thing, see how close to 0 it is in between for that one. How does this work? And this is basically, you draw a bunch of lines just with integer slopes. That corresponds to quantization, okay, as far as velocity goes. And then what we're producing here, and this is very important for classical mechanics as well as for this wave mechanics, as you start to match things that are going back and forth in a two-dimensional phase space, you look for the things that are going this way, where they cross things that are going this way. This one has got a slope of 1 over d2, this is some integer, okay, I guess it would be around 8 or 9 or something right there. And then there's 2 of those, and then there's 3 of those, and there's 4. So this thing keeps wrapping around, runs into its point again, and then just keeps going. So this is just a straight line wound around that cylinder, right? With a slope d2, okay, whatever integer that is. And then there'll be others coming the other way, okay, in this particular one, let's say a d1, a slope, all right? Okay, well, they run into each other and make all of that structure. That's really all it is, and that's all the monster mash is. But boy, it's kind of beautiful, and it has all kinds of really funny number theory in it, which I'd like you in the next 5 minutes to see for the first time, and we'll see it again later on. Okay, so the question is where, of many points, but let's just pick the module or something, where does this particular thing with slope d1 run into this thing with a slope d2? Okay, well, it's right there, and then it's going to happen again other places, but that's what we want to do. We want to calculate that. Okay, well, it's just algebra, very simple algebra, using the slope equation. Okay, there it is. Okay, that's his equation in terms of phi, and the time is this way. Okay, and so the idea of these two equations being equal gives us the coordinates of the crossings, and the crossings can either be places where zeros are or where unzeros or peaks are, where something is. But one of the things I learned from this was, if you want to answer questions in quantum wave mechanics, you don't look where the peaks are. You look where it's not, where it's zero. The zeros are more robust and they have more sort of knowledge of what's going on. Okay, so it's not so much that you're here in this room, it's that you're not everywhere else. And we play that game very much here. Now this time, the time that this occurred, which is time is that axis, okay, is given by a very funny fraction. The fraction is called the Ferry sum, after John Ferry in 1815 was trying to figure out the resonances of the, I think, the Bay of Fundy, which has very high tides and all kinds of oscillations in between the big ones. Okay, and the idea he found was, if he found something at 1/3 and he found something at 1/5, he would also find something at 1 plus 1 is the numerator, that's 2, and then 5 plus 3 is 8. 2 over 8, you find something at 1/4 if you looked very carefully. That would be the Ferry sum. It's also the sum if you're grading UP. That's where they had fractions in UP1 on the first few days, or weeks, or months, or maybe their whole life. Okay? But they don't discover what John Ferry discovered. Right? And then, on the other side is, where is the angle? What is this actual place, the coordinate that comes in? Well, you solve the thing for that as well. And this is a cross product discovered by somebody named Ford in about 1938. It's a funny kind of cross product divided by the sum of the denominator slopes that are assigned to each of those green, and then another number, D1, assigned to the brown. Okay, so these are important numbers, and here is the way to analyze it. That's really cool, and we're making a big fuss about this, and this is in Kim Phys letters. I mean, what is it doing there? But my student Lee was very good at seeing some things about this. And the basic idea is, if you're going to play with fractions, why not plot the numerator versus the denominator? Okay? So to understand a Ferry sum, say you're doing right here V0, 1, V0 is 0, 1, okay, that's 0 over 1. The V1 here is 1 over 1, and this is 1/2 right here, okay? A Ferry sum is simply a vector addition of those two. V0 plus V1 gives you 1, 2, okay? In other words, it gives you something that has a slope of 1 to 2. It points right at 1/2. So here's a real line up here, and here's a map where we're going to find all of the rationals with a denominator greater than whatever this graph is. Okay? And then it keeps going. It goes forever. You can get all the rational numbers mapped out by doing this funny sort of numerator versus denominator plot. Now, the unit circles, these two unit circles are the start of this thing. And what we're interested in is the vector V2 that comes from the Ferry sum of these two fractions. It's 1/2. It's the vector sum of those two, as I said down here. And then what you do is you look at that and you draw a line from the center of this great big circle through the intersecting point of the Ferry vector that points at 1/2, and you'll point at the center of the next circle that's tangent to those two circles. That's what's going to happen. It's pointing to the center of the next circle that goes with 1/2. Okay, that's the forward 1/2 circle right there. Now, how many people here have seen the movie Titanic? Anybody? Hands? Just about everybody. The connection between the movie and this mathematics it should be obvious. Is it?
Yeah.
Remember when the girl had that wonderful, brilliant sapphire diamond? And she posed in the nude for the artist? Now you should never forget this. That's an anthropomorphic connection that you can't wash. Okay? Anyway, it gets better. What if she had more jewels? Let's go for the next fairy sum. This plus this, 1/3. That's the next one. There it is. You do the same thing with these, and there's a magic circle that you get the center of virtually for nothing. And it just gets more and more complicated as you go through. Basically, all of the it's telling you the significance of each one of the resonances that make a pattern over there. These are the rationals that we kind of have well exposed with this particular wave here that has a range, really, it's just 10, plus or minus 10, 11 or 12, depending on how you want to count things here. So anyway, I thought you should know about this. This is just something that's I find really beautiful, both physically and mathematically and cinematically. But the structure that goes inside that, these little rectangles here that are the fractions, they're all being drawn too. Every one of these things has in a rectangle has exactly the fraction that's represented here. So I should say, watch this space. Okay. All right. We have a minute or two, according to my ill-gotten watch here. Any questions? Comments?
I have a question about so what do the circles mean? What's the significance of the circles?
Each one corresponds to a resonance, like the 2/5 or the 2. This guy right here, okay, is quite a bit more significant than 3/7 or any of the 7. There's 2/7. There's 1/7. So right away, what you're doing is classifying the circles according to how they fit between a circle and a line. And let's see if there's anything else I can mention. The size of those circles is the square of the, one, in other words, relative to this thing, that thing is 1/2. It's got a radius proportional to 1/4, and then this one 1/9, and this one 1/16, and so forth. So you square those to indicate how much of a fuss. Obviously, 1/4 makes a big fuss here, but it doesn't appear very often. Here we're looking at 2/7, which would be exactly the same as 1/7 down there. And the 7ths all have 7, count them, 1, 2, 3, 4, 5, no, something's happened. I missed 2 there somewhere, but basically 7 lumps of a certain height. So the circles are related to this guy. The 5ths correspond to something of a certain height. And basically we're just conserving probability. The area would be the measure of the probability, the integral of the curve. Yeah. Good question. Anything else? Well, this is something else to play with. So far, we're trying to figure out what happens now when the wave expands at 2 dimensions. Now you're talking about angular momentum calculus, and we put that in that paper, and we're still puzzling that. There's all kinds of weird things going on there. Okay, well, we'll have a good Labor Day. weekend. We'll see you on Wednesday next week.